Have you ever just stopped in the middle of a game and wondered how they actually do it? How modern video games manage to simulate perfectly realistic water, glossy brushed metal, or frosted glass, and do it so incredibly fast? I mean, we're talking about calculating complex physics, billions of light bounces, and crazy material properties, literally in the blink of an eye. The ultimate stakes here are entirely about tricking the human eye, creating an illusion so flawless that our brains just accept it as reality. But seriously, how on earth does a computer pull that off in just 16 milliseconds?
Well, let's dive right into this explainer. Today, we're unpacking a really fascinating PhD thesis by Giorgio De Magistris from Sapienza University of Rome. And it is all about the magic and the math of real-time rendering. This research is sitting at the absolute cutting edge of computer graphics, tackling the monumental headache of rendering reflections and refractions in real time.
So, here's our roadmap for today. First up, casing photorealism. Second, the hidden physics of light. Third, the real-time rendering bottleneck. Fourth, the screen space illusion. And finally, next-gen rendering breakthroughs.
All right, let's kick things off with part 1, chasing photorealism and the quest for perfect illusions. So the ultimate constraint we're dealing with here is time, specifically 16 milliseconds. To put that into perspective, think about the movie industry. When they're making a massive CGI blockbuster, a single frame of animation can literally take hours, sometimes days, to render on a huge server farm. The computer has all the time in the world to calculate exactly how every single photon of light is bouncing around a room. But interactive video games? Yeah, they do not have that luxury. To give you a smooth, fluid 60 frames per second, the computer has to calculate the whole shebang, geometry, textures, lighting, your controller inputs, in 16 milliseconds.
That brings us to part 2, the hidden physics of light and the rules of the digital world.
Okay, so to understand how light interacts with stuff in a game, we rely on something called microfacet theory. And I know that sounds like a super intimidating academic term, but it really just describes how we fake microscopic bumps on materials. Because in the real world, whether it's brushed metal or a piece of frosted glass, absolutely nothing is perfectly smooth at a microscopic level. Now, actually calculating the exact shape of every single microscopic bump would completely melt your computer. So instead, microfacet theory uses a clever statistical model. It basically says, let's treat a rough surface like it's made of millions of tiny, perfectly flat microscopic mirrors, or facets, all pointing in slightly different directions.
This visual perfectly nails it. See that flat black line? That represents the overall surface normal, just the macro-level, general direction the object is facing. But look at the jagged blue line. Those are the microsurface normals. So even if a wall looks totally flat to us, zoomed way in, it's covered in these tiny, jagged bumps pointing everywhere. When light hits this, it doesn't just bounce straight back. It scatters based on how those tiny blue microfacets are angled. And that right there is exactly what makes a material look matte or rough.
Now here's where our really harsh reality of physics kicks in. Occlusion. Because the surface is so jagged, some of those tiny mirrors actually get shadowed or totally blocked by the bumps right next to them. So light hits a bump, and before it can reflect back out to your eye, smack, it crashes into another bump. We call this masking and shadowing. And trying to calculate exactly which microscopic bumps are blocking other microscopic bumps in real time, it is a massive mathematical headache.
Which leads us perfectly into part 3, the real-time rendering bottleneck and our race against time.
The core of the problem really comes down to how the computer is doing the math. So let's pit path tracing against rasterization. Path tracing is basically the holy grail of graphics. It physically shoots virtual light rays all over a scene, tracing them as they bounce from object to object. It gives you perfect, physically accurate lighting, but it's painfully slow. On the flip side, we have rasterization. This is the lightning-fast method pretty much every video game relies on. It's incredibly fast because it processes geometry independently, but because it's doing that, it has to rely heavily on faking it with approximations. Just check out the stark contrast between these two rooms. The one on the left is lit only with direct light. Notice how the shadows are just completely pitch black? The light comes through the window, hits the floor, and boom, it stops. But in reality, light bounces. It hits the floor, bounces up to the walls, and softly lights up those dark corners. That bounced light is called global illumination, which you can see on the right. Calculating all that complex bouncing is exactly what the speedy rasterization method struggles with, simply because it doesn't understand the context of the whole room.
Let's actually walk through the steps of a standard rasterization pipeline real quick, like what you'd see in WebGPU, to see why that happens. First, the computer gathers the input, processes the vertices, and then hits step 3, rasterization. Here it projects 3D triangles onto a flat 2D screen to figure out which pixels they cover. Then it runs a fragment shader to color them in. Now this is blazing fast because it processes every single triangle entirely on its own. But there's the catch. Because it's working independently, a triangle has absolutely zero idea what's happening to the triangle right next to it. It doesn't know if a red wall is bouncing red light onto it. So yeah, it's fast, but it's completely blind to global lighting.
And that brings us to part 4, the screen space illusion, aka the ultimate cheat code.
So if video games are using rasterization, which is totally blind to bounce light, how are we getting those gorgeous, shiny puddles and mirrors? Enter a brilliant little cheat code called Screen Space Reflections, or SSR. Instead of doing the agonizing math of tracing 3D light rays bouncing around a giant virtual city, the computer just looks at the flat 2D image it has already drawn for your screen. Think about it. If you have a shiny puddle on the street, the computer just takes the pixels of the buildings that are already visible on the top half of your TV and literally just flips them upside down onto the puddle. It is faking a 3D reflection using nothing but 2D screen data. It's so wildly efficient.
But of course, a cheat code like this comes with some pretty glaring flaws. Honestly, think of it kind of like wearing a blindfold. SSR can only reflect what the camera can currently see on the screen. So if an object is outside your field of view, like say a huge skyscraper right behind your character, it is not going to show up in the puddle in front of you. Or if an object is occluded, meaning something else is blocking it from the camera's point of view, the reflection just instantly breaks. If the camera can't see it, it won't reflect it, and you end up with these really ugly, jarring gaps in the illusion.
Which finally brings us to part 5, next-gen rendering breakthroughs. Let's look at how this thesis actually solves these problems. The first massive triumph presented in this research is the two-camera SSR method, and it's such an elegant aha moment. If the main problem with screen space reflections is that it can't see what's behind the player, why not just add a secondary rear-facing camera? By rendering a super lightweight, simplified version of what is behind the player, the game suddenly has screen data for the entire 360-degree environment. So now, when a reflection ray shoots off the edge of your screen, it doesn't just fail and vanish, it seamlessly grabs the data from that rear camera. It vastly improves the realism and keeps the world feeling grounded, all without the massive performance drain of full 3D ray tracing.
And that brings us to the second big breakthrough: fast screen space refractions. Because look, reflections are one thing, but refractions, how light bends as it travels through transparent stuff like water or thick glass, are notoriously tough. This thesis maps out a highly efficient way to fake volumetric refraction in real time. It uses your view position and the surface data to calculate a bent refracted ray, marches that ray through the screen's depth buffer to find exactly where it exits the glass, and then, get this, bends it again. It creates these stunningly realistic transparent materials that actually react to surface roughness, which has historically been way too expensive for standard game engines to handle.
Ultimately, the success of this research really comes down to one specific harmony. I love this quote from the thesis. The results highlight the balance between physical accuracy and computational efficiency, making these techniques suitable for real-time applications like video games. And honestly, that perfectly sums up the core takeaway of our explainer today. Graphics engineering isn't just about forcing perfect physics into a computer. It's about knowing exactly what corners you can cut and how to cheat so intelligently that the player never even notices the trick.
So, I want to leave you with a final, kind of provocative thought here. By using these incredibly ingenious methods like two-camera SSR and fast screen space refractions, the gap between the blazing speed of rasterization and the perfect lighting of path tracing is closing, and it's closing fast. As these rendering cheats become flawless, and as that 16-millisecond illusion becomes mathematically indistinguishable from reality, are we eventually going to lose the ability to tell digital reality from the physical world? It's something to think about. Thanks for exploring this fascinating topic with me today, and hey, keep questioning those illusions right in front of your eyes.